Okay, let's get the show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1108. Let's actually get into it. We introduced a new idea last time, and
recording in progress.
Did this thing update? Okay, there we go. Let's look at last time. We used this example with a basketball player taking free throws to introduce something called a binomial probability. So we figured out a nice formula to describe this situation was this formula over here. And we know that this formula applies whenever these three situations are fulfilled. So this is just something that you know to look out for now because I told you about it. So pretty much what's going to happen is if you are looking at a problem and you realize that what's going on here is that we're just doing the same thing over and over and over again. Each time it's independent of the other time, all the other times. And there are really only two, specifically two. I don't know if I should like underline that. It's binomial for a reason because there are two, right? By for two. There are specifically two possible outcomes, two types of outcomes, where one kind is classified as success and another kind is classified as failures. And if we were to count the number of successes that happen in the end trials, then the probability of us seeing that many successes is given by this formula. So when we had this basketball player just throwing free throws, he's doing the same thing over and over. We're told here that they're all independent, which in real life they might not be, but for the purposes of this problem, we assume they are. And we want the probability that he will make 10 shots or make 2 shots or make between 3 and 5 or at least 1. What you should realize here is that, yes, 1, he's repeating the same process over and over. 2, they're all independent. In this case, we're just told flat out that they're independent. And 3, there are only 2 possible outcomes. He either makes the shot or misses the shot, right? There's no other thing that can happen in this experiment. He either gets it or he doesn't, right? There's either success or failure. And by the way, success and failure in this context is very general. Success is just whatever you're looking for to happen, right? If I wanted to write this problem in terms of how many he misses, then I could call him missing a shot a success and then him making a shot a failure, right? So it really depends on the interpretation that you want to put on the problem. Success is just the thing we're looking for to happen, and we want to know how many times that thing happens, right? So that's a success. And whenever there's just 2 things that could happen, where one of the things that we're interested in, that we're looking for it to happen, that's your success. The other thing is your failure. And whenever you're in that situation, you have a binomial probability, as it's called, which means this formula that we derived automatically takes effect. Now, the solution to the basketball problem is just using this formula. So here, we know that he's just repeating something 10 times, where the probability of success is 70%, therefore the probability of failure is going to be 30%. And we have independence, so these are binomial probabilities. So if X is the number of successes, we can find the probability that he makes all 10 by this formula, which I think I actually worked out what these guys were as percentages. So let me just put those in. Right? So N is 10 and K is 10, P is 0.7, Q is 0.3. Plug into this formula and that's your answer, right? So this was roughly, there's a 2.8% chance that he's going to make all 10. So if you know someone who they make 7 out of 10 shots that they take, very usually, and if they're taking 10 shots, what is the probability that they're going to make all of them? It's about 2%. Well, almost 3%, right? What is probably the probability that he makes exactly 2 shots? Well, that one is just you choose k equals 2, n equals 10, p equals 0.7, q equals 0.3, and you would get this formula. That is actually even smaller. That's 0.14%. There's less than 1% chance that he's only going to make 2, exactly 2, no more, no less. What's the probability that he makes between 3 and 5? Well, making between 3 and 5 would mean he makes 3 or 4 or 5. Now, of course, he can't make 2 of these at the same time, because if he made 3, then he didn't make 4 or he didn't make 5. So these are all mutually exclusive. And so the or translates to plus. And then we can just apply this formula 3 different times using k equals 3, 4, and 5 respectively. And that will give you around, there's a 14% chance that he would make between 3 and 5. Now, what's the probability that he'll make at least 1? You have someone with a 70% success rate. The chances are that they'll make at least 1 out of 10 should be pretty good. So at least 1 would mean greater than or equal to 1. So it's 1 or 2 or 3 or blah, 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 all the way up to 10. That's a lot of things to calculate. I would instead use the complement. The complement is just x equals 0. He makes none of them. So we just use 1 minus the probability that he makes none of them. And that is going to be huge, 99.9994%. Right. So there's like a 99% chance, basically certain, that this guy is going to make every shot. Not every shot, that he's going to make at least 1 shot or more. He's going to make 1 or 2 or 3 or 4, right? This is a guy that makes 7 out of 10 regularly, right? So the chances that he's going to get at least 1 should be pretty good. And using the binomial formula, you actually realize that that is the case. Now, regarding that, I left you with another problem to do, which is something that we're going to do now together. Very important problem type. This is actually a past exam problem on a final. I probably put it on a test way back in the day, but I've also put a problem like this on a final. Knowing how you would do in a test or a final, this problem would be a pretty good estimate. That being said, these examples that I'm going to be doing is coming from probability set 3. I posted it here in the notes for your convenience. And this problem that I'm going to do for you guys is problem 16 in that problem set. Tomorrow, I'm also going to be doing 10 and 11. And that is really going to kind of end probability for us. And we're going to go into statistics. We're going to go into the very basics of statistics. We will do, well, what are statistics, not necessarily how to collect them, but once you have them, how you can start to analyze them using charts, using things like central tendency, like mean, the average, mode, median, talking about the spread of the data, standard deviation, variance, all that kind of good stuff, and why these things are important and how you can think about them. So that's what we're going to actually start. And yeah, I think that's all we need to do for statistics. So it's the very basics of statistics, sort of like just the stuff that you would need for the project, which I wouldn't really expect you to have to go farther than that. So I'll actually do things like scatter plots as well. I might talk about a regression line, but I'm not going to give you, I won't expect you to know how to find one. But yeah. So that being said, let's actually move into what we're going to do today, which is try this one. So let's actually get through this one together. My notes here. Yeah, so this is the first thing I want to do. Okay, so let's read together. Blood types O, A, B, and AB occur in the population with these frequencies: 0.43, 0.41, 0.11, 0.05. These are the blood types. Just assume that these are all the blood types in existence. So there are 4 blood types. You can be a type O, A, B, or AB. And the chances of you being type O is 43%. The chances of you being type A is 41%. Chances of you being B is 11%. And the chances of you being AB is 5%. On top of this, there's a blood protein factor called the Rh factor. There are 2 varieties. They're denoted positive and negative. And so you can have a blood type with a positive or negative protein factor. The protein factors occur with frequency 0.86 and 0.14. So chances are within any blood type, there's an 86% chance that you're a positive, and there's a 14% chance that you're a negative. So if you have blood type A, there's an 86% chance that you're A positive. There's a 14% chance that you're negative, etc. Now, this chart here gives us some data about who the various blood types can donate blood to and who the various blood types can donate blood from, can receive blood from. So, for example, if you're an A positive is your blood type, then you can donate blood to someone who's also A positive or who's AB positive, right? So if someone needs blood and they are blood type A positive or AB positive, then you as an A positive person can donate blood to that person. The other people can't, right? So we're just going to assume that these tables are true. I think this is actually true data, but don't quote me on this. For the purposes of this problem, we're just going to assume everything here is true. Now, as an A positive person, what if you're the one who needs blood, right? So you walk into a clinic, you need to get some blood. Then the kinds of blood that you can receive would be A positive or A negative or O positive or O negative, right? O is a very versatile blood type. People of type O can donate to a lot of people, but yeah, but you as an A positive person can receive blood from these people, right? And then there are all the other blood types there, right? So now let's actually answer some questions now. What is the probability that a random person can donate to a person that has blood type A positive? So let's say you're A positive, you go to the clinic, you need blood. Sorry, sir, we ran out of blood. And just in the nick of time, thank the heavens, a random person walks in and says, hey, I want to donate blood, right? What is the chances that that random person that just walked in will have a blood type that is useful or can be used to give you blood, right? That's what this is asking. Okay, so let's actually look at that. What does that mean? So, the DB, the event, the person can donate blood. Okay. Now, probability that that can occur is the probability of what? According to this table you would look up, they have to be A positive or A negative or O positive or O negative, right? So this is A positive or A negative or O positive or O negative. Now, of course, these guys here are mutually exclusive, right? You can't have both types of blood, right? You have to have, you can have blood type A or blood type O. And once you have blood type A, you can either be positive or negative. Another thing you can realize here is that you don't even really need to care about the positive or negative, because positive and negative make up 100% of the A people. So this is just type A in general. And this is just type O in general. So we don't really need to worry about the positive and negative parts. It's possible that we did, though. So for example, like if you're an A negative, then you would need someone who's A negative or O negative. And so you need the probability of them being A times the probability of them being negative plus the probability of them being O times probability. Okay, so you get it. So that's what we need. So really, the random person who walks in, we just need them to be blood type A or O of any protein factor, right? Now, again, these are mutually exclusive. So this just means they're of blood type A. We can find the probability of that by adding the probability that they're blood type A to the probability that they're blood type O because of how mutually exclusive works. And so this is going to be 0.41 plus 0.43. That's 0.84. So if you're an A positive person and you walk into a blood clinic, you need blood, and someone comes in and randomly donates, there's an 84% chance that that person can donate blood to you, which is awesome. That's pretty high. Yeah. Now in B, you'll notice that things get a little bit trickier. Now we're doing multiple things like this. So, all right, you're still the same A positive person and you need blood, right? And they don't really have blood for you. But luckily, a bunch of donors just showed up. In fact, 8 of them showed up. 8 people show up wanting to donate blood, right? Each person can only donate 1 unit of blood. You happen to need 5 units for whatever condition you're in, right? Don't worry about how much a unit is. Just know that you need 5 units and each person is only allowed to donate 1 unit because you don't want to affect their health, you know, so that we'll only allow them to donate 1 unit. Now, here are 3 questions. What is the probability that at least 1 unit of blood can be found for the patient with A positive? Another question is, what is the probability that the hospital will obtain all the blood that it needs? And there is, of course, an admonition here. Be careful to consider all possibilities. We're going to talk about that. Because that's actually different from the second question, which asked, what is the probability that the hospital will obtain exactly the amount of blood that it needs and no more? So obtaining the bloods that obtaining all the blood that it needs and obtaining exactly the blood that it needs, these are 2 different things. And we'll see how in a bit. Now, at first glance, this problem might seem very complicated, but then you remember, oh, last class we covered this thing called binomial probabilities. And if we think about this process here, you will notice that it fulfills the conditions of a binomial probability situation. What are we doing? We're repeating an experiment. What experiment? 8 people come in to donate blood. We take their blood and we test it. Can they donate to you? Right? So that's an experiment that's being done over and over. It's being done 8 times over, right? There are only 2 possibilities in this situation. Either they can donate to you or not, right? Only 2 outcomes, right? You can get blood from this person or you can't. There's no other possibility, like yes or no. And lastly, these are all independent, right? If we're assuming all these people randomly walked off of the street, we don't assume they're related to each other or anything. Like one person's blood type has no influence over another person's blood type. It's completely random and in the sense that it's independent of each other. So we have independence. We have something that we're repeatedly doing over and over, and that thing has 2 possible outcomes, success or failure. Success is that we get a unit of blood that can be used. Failure is that we don't, right? So this is a binomial situation. So we're repeating an experiment. Testing to see if a donor's blood can be used for the patient. Okay. Right? And that's happening over and over. In fact, it's happening 8 times, right? So here, your N, the number of times this experiment is being repeated, is 8. There are 8 donors. What is the probability of success? Well, we calculated that in part A. It's 84%. So this is from part A. This is number of potential donors. Number of donors being tested. Okay. Now, of course, if P is that, Q would be 0.16. So probably a failure. This is just, 1 minus P. And we know it's binomial because only 2 possible outcomes. Yes or no. Yes will be a success. No would be a failure. And these are independent. Okay. So here N is 8, P is that, Q is that. Now, once you actually figure that out and you let X equals the number of people that can donate, now we're in business, right? So in part 1, we'd realize that the probability that a random person can donate, at least one person, at least one unit can be found for the patient. It means at least one person would be able to donate blood. So what this is really asking is that the number of people who can donate to you must be greater than or equal to 1. Right? That's what we want. Now, what is the probability that X is greater than or equal to 1? So the probability that X is greater than or equal to 1, well, that's just the probability that X is 1 or X is 2 or all the way up to X is 8. So that means one person can donate, or 2 or 3 or 4, all the way up to all of them can donate. That's a lot of calculations. I'd rather do the complement. Which is, you can't find at least one that can donate, which means there are no people who can donate, right? So this is complement. And now what is that? Well, according to our binomial formula, this is going to be 8 to 0 P to the 0 Q to the 8 minus 0. So this is just going to be 1 minus 0.16 raised to the 8. And that's roughly a 99.99%. Or 0.9999, right? Yeah, so you're A positive, which means any random person walking in, there's an 84% chance that you're going to be able to get blood from that person. What are the chances that if 8 people walk in, each of them having an 84% chance of donating to you, that you'll find at least one person who can donate to you, pretty high. Right? It's almost certain that you'd get at least 1 unit of blood, right? Which is great for the positive person. How great it is, we don't know yet, because we don't just need 1 unit of blood. We actually need 5 units of blood. So let's actually get closer to that. What is the probability that the hospital will obtain all the blood that it needs? Now, what you have to recognize here, what you have to be careful about, is that getting more than you need is the same as getting all that you need. So for example, we know we need 5 units of blood. If we get 6 units of blood, do we have all that we need? Yeah, and more, right? If we got 7 units, do we have what we need? Yeah, and more. If we got 8 units, do we have what we need? Yeah, and more. So this is actually asking for, you get at least 5, right? You need 5. You need 5, and you'll take more if you can get it, but you need at least 5. And so that's what problem 2 is talking about. So here, we want the probability that you get at least 5. So now the probability that we have at least 5 is the probability that we get 5, or the probability that we get 6, or the probability that we get 7, or we can get 8 people to donate. Now, each of these have their binomial formulas, where we're just changing the k. So the first one is going to be 8 choose 5, p to the 5, q to the n minus 5. This one's going to be 8 choose 6, p to the 6, q to the n minus 6. Then we're going to have 8 choose 7, p to the 7, q to the 8 minus 7. Then we're going to have 8 choose 8, p to the 8, q to the n minus 8 minus 8. So you can do that. You can plug into your calculator, which I definitely recommend you try. What you should get is this 0.973. So there's a 97.3% chance of that happening. So if you're type A positive, you need 5 units of blood and 8 people walk in to donate blood right then and there. There's a 97.3% chance that you're going to get the blood you need. So, I mean, don't panic unless you're very unlucky usually, but that's, you know. But yeah, 97.3% chance you're going to get what you need. Now, if you look at part 3, what is the probability that it will obtain exactly the amount that it needs and no more? Which means you want the probability that you'll get exactly 5 units of blood. No more, no less. So you can't get 6 or 7 or 8. You can't get 4 or 3 or 2 or 1 or 0. You have to get 5, exactly 5, right? It's just going to be like, we just made it, just enough, right? We got 5. So part 3 is not at least 5. Part 3 would be equal to 5. So we want the probability that x would be equal to 5, which again, we can use our formula. And that is a little bit less than 10% chance that we'll get that, 9.592. That's the probability that you'll get exactly 5 units of blood on the nose, right? So you have what you need. But it's not all the possible ways that you can have what you need. You could get more than that and you'll be satisfied. Yeah, so that's another example of binomial probability. So there are word problems. Sometimes you're reading probability problems and you'll realize that, hey, the same thing is happening over and over. There are only two ways that this could go, really, this way or that way, like yes or no, success or failure. And each time it happens, you assume it's independent from the other, or you have reason to believe that, or the problem tells you that that's the case. Then you're like, oh, I can use this formula to find probabilities. It's a very nice formula. And it actually shows up quite often. The binomial probability formula is something that's used very often. It's very, very important.
Professor, can you just explain again how you got the 0.84 at the top?
Oh, that was from part A.
Yeah.
In part A, we found the probability that you can get what you can donate to a type A positive person. And the person in part B was type A positive.
Okay.
So here, if you're A positive, you can get blood from an A type or an O type. And that's an 84% chance that that will happen. Right,
Okay,
so that's the success probability that any random person can do it.
How did you get the 0.41 and the 0.43?
Oh,
Like,
that was
obviously,
given. That was given in the problem.
Oh, shoot. Okay.
Yeah, yeah. I mean, it's a long problem, and I just read it very quickly. That's fine, but it was given.
Oh, got it.
That's not
Okay.
something I expect you to know.
Got it.
Yeah. So you have the information here about the probability of you having each blood type, as well as who you can donate to and who you can donate from. So I could have asked this a very similar question to this. Just be like, okay, so pretend you have an A negative person and they need 4 units of blood and 11 people walk into the hospital. What is the probability that they'll get all the blood that they need? And then you'd need to find what is the probability a random person can donate to an A minus, means that they have to be the probability of an A minus and an O minus or an O minus. And then you go into binomial. Yeah. Now, there's a notion that we're actually not going to do a lot with, but it's in the syllabus that I need to tell you about this, so I'm going to tell you about it. But we're not actually going to do much with it. The power of this notion that I'm going to talk about really begins to shine when you start doing a lot more sophisticated probabilities where you can apply calculus rules, rules of functions, and things of that sort. And for a function to work, you need to know about a variable, an input variable, and an output variable, and things of that sort. So we try to get the notion of a variable into the realm of probability. And that way we can study probability by what we know about studying functions. And we can do a lot of things with probability that we can do with functions, like apply calculus and things of that sort. But that's way above what we're going to do. But I still need to kind of tell you about this concept. So the X in our binomial probability our binomial probability situation, or maybe I should say formula, in our formula. It brings up an important notion, like important in general. We're not going to do much on this, and that is the notion of a random variable. It's a variable that you want to apply to a random experiment. So definition, a random variable is a function whose domain is a sample space, i.e. the inputs are sample points And its range is a subset of the real numbers. I.e., a random variable x, we often call them by uppercase letters, assigns a numerical value to each possible outcome. That's all it does. You'll notice that the x in your binomial formula does just that. When I say something like x equals 5, right? The output of x is 5. What I'm actually describing is an event. X equals 5 means the event has occurred that 5 people can donate, right? So that event, 5 people can donate, I would plug into the function x, and the output would be the number 5, right? So it's a very straightforward function. It just tells you the number of successes you can have for some event, right? So that's the binomial one. But this can be done more generally, of course. So let's look at some examples. You flip a coin. Let's say you flip it twice. You can then let x equal the number of heads that appear. Then x is a random variable. Because you'll notice what you just did is you actually created a function that's going to assign a number to the events. So for example, we will have the sample space here. With all the possibilities, like you can get 2 heads, or you can get a heads then a tails, or you can get a tails and a heads, or you can get 2 tails, right? And here is like the real numbers. What your x does is it's going to match each event to a number. Now, if I let x be the number of heads, it's going to match HH to the number 2. The event HT will be matched with the number 1. The event TH would also be assigned the number 1. And the event TT would be assigned the number 0. So I take an event and I pretty much use numbers to represent those events, right? And the function that I use to do this, that's called x. Right? So just like when I say x is the number of successes in a binomial experiment, right? Which is the other example. So if x equals the number of successes in a binomial type experiment, where we know that the probability that x equals some value is given by n choose k, p to the k, q to the n minus k, then x is called a binomial random variable. Right? So it's just a random variable, right? And you can realize that its possible outputs are, it can take on 0 or 1 or 2 or all the way up to any output going up to n, which the numbers 0 through n integers is a subset of the real numbers. Okay. That's all I really want to tell you about random variables. It's just a way to assign numerical values to events. And once you can do that, you can actually start talking about probability about events in terms of numerical values, and functions, which now gives you a whole other list of tools that you can use in your probability. So that said, moving on. Here is something that you're definitely going to need to know how to do. And getting to the title of today's lecture, I'll just give you some definitions. There's a topic called probability distributions. So let me tell you what that is. Definition. The probability distribution is, well, for us, it's a table. So if I ask you for a probability distribution, I expect you to draw a table for me. A table which lists all possible outcomes and the probability for each outcome. Really what it is, it's a function, it's another function, where the inputs are the values of a random variable and the outputs are probabilities. So that's just going to be a real number, but definitely between 0 and 1. So what these look like is just a table, which we usually draw it horizontally. So there's some random variable here. And let's pretend it can take on values like x1, x2, all the way up to xn. Then in the second row, what we're going to do is the probability that x takes on each individual value. So we can call that P1, P2, Pn. And what the P's actually are, this is just the probability that x equals x1. This would be the probability that x equals x2, and so on. This will be the probability that x equals xn. Right, so what is the probability that our random variable will output that value? Example. What is the probability distribution of the following? Okay, so here's the first one. Toss of a fair coin. Okay, so that's just, if I ask you, what is probability distribution for a toss of a fair coin? Well, you can say, well, X can output heads or tails. Then I want the probability of X. That's going to be a half or a half. And that's it. That's the table. And numerical values maybe assigned here. So I could say, if it's heads, output the number 0. If it's tails, output the number 1. And then in the top row, I'd have 0 and 1. So that's it. That table is the probability distribution. Here's another example. The roll of a 6-sided die. Right. So here your X can take on several values, 1, 2, 3, 4, 5, or 6. And now you just want the probability that X will take on each value, which we now know, we've known for a while, is just 1/6 for each of them. So that's a probability distribution. Right? We can have another example for the sum of the roll of 2 6-sided dice. Well, if X is the sum, then it can take on values 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. We saw that a while ago. We also know the probability that X will take on each value, right? So this was 1 out of 36. This was 2 out of 36, 3 out of 36, 4 out of 36, 5 out of 36, 6 out of 36. 7 was the most likely, and then it counts down. 5 out of 36, 4 out of 36, 3 out of 36, 2 out of 36, 1 out of 36. Right, so that's a probability distribution for the sum of 2 dice. D, there's something called a binomial distribution. So for that, your X would count the number of successes, and the possibilities are 0, or 1, or 2, or K, or N, right? And what is the probability that X will attain each of these values? Well, here it's going to be N choose 0, P to the 0, Q to the N minus 0. Here it's going to be N choose 1, P to the 1, Q to the N minus 1. Here's going to be N choose 2, P to the 2, Q to the N minus 2, etc. Here's going to be N choose K, P to the K, Q to the N minus K. Here's going to be N choose N, P to the N, Q to the 0. Right? So that's what a binomial distribution would look like. And any probability distribution that you see following that situation is called a binomial distribution. If the numbers for the probabilities can be obtained by that formula, what you're looking at is a binomial distribution. Another definition. Distributions are important for many reasons, but for us, they are useful in finding something called the expected value. All caps. Or it's also called the mean. So given a distribution the expected value of x is defined by this expression. It's called E of x, right? You might also see it called mu, a Greek letter of x. And it's really a sum product. So you take the product of each output times its probability, and then you add them all together. So this is going to be x1 times p1 plus x2 times p2 plus x3 times p3 plus all the way up to xn times pn for this table. There's a shorthand way to write this. It's called the sum of xi pi. I goes from 1 up to n, but you don't really need to know that. So I'll give you one short example, and then I'll leave you guys with a couple examples that we'll finish tomorrow. So pretty much fully worked out, but I'm gonna write it down. Example. What is the expected value of the roll of a 6-sided die? So here we know that distribution. So this means the expected value is going to be, well, 1 times 1 6 plus 2 times 1 6 plus 3 times 1 6 all the way up to 6 times 1 6. So 1 6 is a common term. 1 plus 2 plus 3. We know by a formula, sum of the first n integers, that's going to be 6 times 7 over 2. So that's just going to be 7 over 2, and that's 3.5. Which is a very strange number to associate with the roll of a die. Is such a thing useful? Yes. Basically what that number is telling you is that if you were to roll a 6-sided die over and over and over again, many, many, many times, and you were to find the average of all the numbers that you got, that average is going to get closer and closer to 3.5. And knowing something like that is actually going to be very useful. And a very silly example of how that can be useful, you can try these examples to see where money is actually on the line. Of course, it's gambling, but there's money on the line. And the expected value can help you actually make a decision as to how much money you're going to lose, just know what situation you're walking in, etc. So expected value is very important. It just kind of tells you what is the average outcome in the long run. That's why it's useful. And knowing that is super important in many situations. But for now, we will stop there. We'll do these 2 examples next time and start statistics. So that's it. Yeah, we're over time, so I'll let you guys go. Yeah, I know some of you emailed me some work that you did yesterday. I'll respond to that like right now, and I will see you guys in the next one. Ciao.